All right, thanks a lot. I'm Chris Gruber. I'm going to be talking about Keras. So if you've never heard of Keras, this is a framework for building neural networks in Python. So neural networks, obviously a buzzword. Why would you actually care? Well, it turns out you can do all kinds of stuff, including like automatically tagging images, translation, image segmentation. You can even generate whole artificial textures and immersive worlds. And one of my favorites is this style transfer in the bottom left, where you can take an image and sort of transfer its kind of salient characteristics to another image. It's just a really interesting kind of art project there. So yeah, this talk is going to be about neural networks. And the point is I'm trying to motivate you to actually care about building neural networks and show you that you can actually do it fairly easily using pretty good tools like Python and Keras. So this is a schematic of what a normal neural network would look like. So it's a model that takes input and maps it to some sort of output. And the real important characteristic of it is what's called the depth, which is how many of these sort of layers that you put in a row to basically take your input and do this mapping. So the depth is usually what people talk about when they are characterizing neural networks. So for something like deep learning, which definitely is a buzzword, they're talking about networks that have a fairly big depth. And it's sort of a term like like big data or something, where it's a very relative thing. It's relative to how much can your computer handle. That's what deep learning is, basically. It's a very flexible term. And so these things can get really complicated. This is an image of a kind of a famous architecture that's used for some sort of image processing that was developed by Google. So I'm not really going to be talking about really complicated things like this model, but I will come back to this in a little bit. So the networks I'm going to be talking about have this kind of a structure where every layer is kind of connected to the layer behind it. So you're going to have information feeding into this thing from the left to the right. And similar to any other kind of model, you're going to develop your model and then you're going to introduce a bunch of training examples to fit all the different weights and other parameters of the network. And thereby you generate kind of a generic mapping from input to output. And one important thing to note is that your output could be really much of anything. These kinds of networks are able to do anything from regression to classification to image tasks, or you can even output things like sequences, or it can do time series modeling. So it's an incredibly flexible framework for doing any kind of sort of generic mapping like that. So if you zoom in to what one of these network nodes looks like, it has some nodes connected to it from the left in the preceding layer, and then it has nodes connected to the right. So each of these nodes is going to have an output that's labeled by X. It gets weighted based on a parameter that connects it to this node. We're going to sum up these inputs and the weights, do some sort of calculation, and then pass that on. And so the context kind of matters here, because these X's could be your initial input, or they could be a previous layer, and then the output could be the output of your model, or that could be passing it to another layer. But in general, this is what's going to be happening in each of these network nodes. It's just a simple kind of summation and then a function. And the real power of these is that you're performing this function, passing it off to another thing that's going to perform a function. So you're basically taking functions of functions of functions. And that's what really gives it this power to capture kind of nonlinear relationships in data and things like that. So this is really where the power of this kind of model comes from, is this kind of recursive structure like that. There's finally some words in this talk. So Keras comes in because it's a high-level API that works with Theano and TensorFlow and some other frameworks that really streamlines the API, makes it a lot faster to code. And it has a very similar syntax to scikit-learn. So if you know how to program models there, it's pretty easy to go over to this framework as well. It has implementations of all the common stuff you would ever want, like convolution layers and other kind of advanced neural network features. It also has all kinds of precompiled models and data sets. And in fact, that GoogleNet image that I showed, that incredibly complicated network, you can actually just import that pre-trained into your model, which is pretty cool. And you can actually build around it and set this big network as being a black box, as an untrainable thing, and you can build around it and train your model to use this as a component. So it's pretty cool, really, really flexible. And so all the standard components you would use, like activation functions and optimizers and callbacks, all that stuff is predefined, but then you also have the ability to use templates to custom define your own. So it really balances this like flexibility and convenience. In simple networks, which is what we're going to be looking at here, usually it's one line of code as one layer, which is a lot faster than using something like pure TensorFlow. And so additionally, you can actually intersperse TensorFlow code with your Keras code, which is cool. And also, the documentation in the community are really good. So I all around recommend this over other frameworks I've used for neural networks like H2O or pure TensorFlow. It's really a really good thing, in my opinion. So I'm going to be showing not yet. This image, which is probably completely unreadable. I thought this screen was probably going to be bigger. This is a sample of just some of the different architectures that you might encounter when you read about neural networks. And all of these things can be developed using this tool. I included 2 pages of links and other resources. So if you are interested in getting started with Keras, there's a lot here. All kinds of documentation and blog posts and that kind of stuff. So I'm going to be showing a quick demo of building a neural network and showing how easy it is to do that in this framework. So what we're going to be doing is using what's called the sequential class, which is kind of a generic container where you can build your network line by line. And so we're going to construct a network that has 10 nodes in each layer, and it's 3 layers deep. And so we're going to train this using the MNIST data set, which is a data set of handwritten digits. It's kind of trite because that's what everyone does, but the nice thing about it is that you can benchmark your model with things in the literature, and you could. It's a standard data set, and so it's an easy way to see how good your model is. So what we're going to do is, thank you. We're going to expose this untrained model to handwritten digit data. We're going to feed it in, and then we're going to tell the network what the answer is. Do that a few times so that in the future, when you have an unseen new sample, your network will be able to tell you with confidence what digit you've shown it. Okay, so we're going to load in our digits. This is a sample of what the handwritten digits look like. They are a 28 by 28 pixel image. So it's a fairly rough picture of a handwritten digit. And our data set is 60,000 of these in the training set and 10,000 for the testing set. Yes. Okay, so here's where we actually define the network. So we basically instantiate this container called the sequential, and then we add our layers one by one. So we're adding 3 layers with 10 nodes, and we're specifying some basic stuff about it, like the activation function and then the input shape. We then fit our model. So this is similar to scikit-learn. You develop your model, you just do this fit method. And so what we can do is take this and predict a few of the digits and show what the actual digit is and what the model thinks it is. So as you can see, there's 9 out of 10 of these, it's spot on. It's only this weird 5 or 6 looking thing on the right that it gets wrong. So it's actually, from this small sample, looks like it's kind of comparable to a human accuracy rate. And in fact, it's about 92% accurate. Gets about 92% of the testing set. So these are ones that the model never saw while it was training. These are things that are purely inferred by the trained model. And so before you say, okay, 92%, that's okay, but wake me up when you actually have a human-like ability to look at these. But in fact, if you look at some of these handwritten digits, I don't know what preschool these people went to, but some of these, you can tell it's a 7 or a 1, it's a 4 or 7, a 9 or if you look at what the actual the solution is, some of them are fairly reasonable, I guess, but so obviously these are cherry picked, but just to demonstrate that it isn't actually as straightforward as one might think. So getting, I think the human level on this task is something like 97%. So just with this few lines of code, we've been able to get something that is a 92% accuracy on this task, which is pretty good. And this is a fairly simple model, and I only trained it for about 6 seconds. So if you were doing something that's an actual, something at your job or something, you could do a much better job than this. It's just wanted to make sure I could rerun this in case disaster struck during this talk. And that's it. Jerry?
Yeah, hey Chris. So some people in the back here asked, I'm assuming you're going to make your slide deck available to on meetup.com so people can take a look at greater detail.
Sure. Yeah, and like I said, I listed a few pages full of links and stuff as well, so I'll make sure that this is available to anybody who wants a copy.
Can you include a Python notebook?
Sure, yeah. Python notebook will also be involved. Yeah.
So you mentioned I only let this train for 6 seconds. Generally, if you let a sufficient amount of data continue to train, do you see better results?
Typically, yeah. Yeah, so the question was, I obviously didn't train this for very long, and what are the pros and cons of training it longer? So yeah, obviously, if you train it for a longer time, you can get it to map the input and output a little better. But like any other model, you risk overfitting. Neural networks are actually kind of notorious for overfitting. Like they'll always look like they're doing better on the testing set, but at some point the trade-off is no longer worthwhile. And so I didn't get in any of the complicated details, but there's actually mechanisms to sort of monitor how well it's generalizing, and you can do like an early stopping procedure if you need. Dan? Right, so Dan's question is, this Keras framework can interface with things like TensorFlow and Theano. One of the beautiful things about it is that the API is identical. Once you set the parameter to tell Keras what backend you're using, it doesn't have any difference whatsoever. I could take this code and run it on, this was actually Theano, you could run it on TensorFlow without any modifications. And the only kind of caveat to that is that if you are taking kind of raw TensorFlow code and interspersing it with Keras, that obviously is a danger. So, but you can make your code completely independent of the particular framework by using just kind of a pure Keras model.
You can go first. For exporting
Sure. So the question's about how do you save models? There are mechanisms to save it as a H5 format, so you can save. I think you save the model and the weights separately, but it's a few lines of code to either save or read one back in. So, Jerry.
As far as Keras and API changes of this back end, I know that some of the data scientists I work with are talking about issues they're having between like TensorFlow 1.4, 1.5, and stuff like that. How well does Keras abstract that away? Is there like breaking changes because it's a vastly new field, or is it pretty solid?
So the question is there any danger that Keras will be affected by kind of back-end changes, like if TensorFlow comes out with a new version? As far as I know, I've never read about those kinds of conflicts happening, but to be honest, I don't have a kind of a comprehensive view of that. But if anything, they are kind of onboarding more frameworks, like the Microsoft one is actually brand new. So as far as I know, it's not a major issue, but sure, one could Google it. Yeah.
Do you know how that model accuracy compares to others, like on scikit-learn?
So the question is how this model would compare to scikit-learn style models. So in principle, you could use any model that would do classification for this, because you're feeding in the raw pixel data and telling it what classification your training example is. So in principle, you could use something like support vector machines, but off the top of my head, I don't know how the performance compares. I know that in published results, neural networks are usually the top of the field by a slim margin. It might be 98% for a support vector machine and 98.1 for a neural network. They're usually fairly neck and neck.
Was there one more question?
There's a lot of freedom in Keras to choose like different initializers, different optimizers, different activation functions, different batch sizes. Do you have kind of a go-to set of parameters that you use, or do you just sort of all the different possibilities?
Yeah, so the question's about hyperparameters. So neural networks have a lot of different kinds of parameters you can set that are kind of global, the architecture of the network and things like that. Usually the defaults are typically pretty good, but usually what I would do is run some sort of grid search or random search or something like that. And to a degree, your problem is going to dictate what kinds of hyperparameters you can choose. Like you would never choose certain activation functions for certain target variables, for instance. So you can narrow down the field a little bit. But typically, I would set up some kind of automated procedure to choose hyperparameters, run the model, rinse and repeat. That isn't an option sometimes when you don't have the computational power to develop 10 or 100 models. And in that case, I think it's trial and error, honestly. Yeah, there honestly is kind of an art to fitting neural networks and choosing the right parameters and things. There's really not a very good set of kind of like heuristics out there, unfortunately. Yeah, Dan?
So in addition to obviously the model built into scikit-learn, it has a bunch of tools for sort of a whole pipeline, like has like for feature extraction and all of the feature selection, all that type of stuff, assessing the model. Does Keras work with that? Does Keras have its own sort of set of tools beyond just the model itself, like if we're doing something like grid search?
Yeah, so the question is about evaluating your models and whether it has kind of the same constructs as scikit-learn. Some of them you can actually just use scikit-learn. Like for example, when you're looking at calculating a cross entropy score or something like that, you're feeding in like two lists of numbers. So a lot of these are generic enough that you don't actually need to use scikit-learn, but a lot of the Keras functionality does have some basic stuff, like you can track accuracy and whatnot when you're training your model. I don't think it's as sophisticated as what's in scikit-learn, but yeah. Yeah, I mean, one of the other things I'll add in is that one of the downsides of using neural networks is that it's not as transparent as using something like regression or something like that. You don't necessarily know what all the calculations in the neural network are necessarily doing. Like, you don't know what kinds of abstractions are being generated in the inner layers. So to a certain degree, you're kind of limited in what kind of analysis you can do of your model. Anyone else? Just one more.
For people wanting to like learn more and get good at using things like Keras and its alternatives, how would you recommend dividing one's focus into learning the implementation of the specifics of Keras code or TensorFlow code or whichever, versus learning exactly how it's doing what it's doing and what the theoretics are of it?
Sure. So the question is, how should you divide your time if you're going to learn how to use this framework? I think, like a lot of things, it really helps to have your hands on the keyboard. So I would recommend doing things in parallel. Building a simple model while you're learning what different activation functions there are and things like that. So you can actually have a hands-on look. I would argue that some of the more granular details, like how stochastic gradient descent works and all this other stuff, you can develop a good model without having a really firm understanding of some of these considerations. So some of these things I think you should just learn gradually. You don't have to know all the math to build a model. I would say that's similar to something like support vector machines in scikit-learn. You don't necessarily know precisely how it's calculating the width between the points and stuff like that. You can still build a good model. So yeah, I guess in short, I would say do things in parallel. Always have your hands on the keyboard, but always keep learning. Amen.